Lab 10, and we're going to focus on energy and power units. So when you're looking at this lab, the one thing that you really want to think about here is that when you say the word energy, it has a very, very similar process as momentum. If you say the word energy, this is meaningless. It has no meaning at all. So the way we define the word energy is we use this thing called the work energy theorem. And what the work energy theorem tells us here is that when somebody does work, there is a change in energy of the system. In other words, this is how we define the term energy, change in energy. So this term is meaningful. So when you compare these two terms here and here, the physical way to interpret what energy is how much work did you have to do? So in other words, if there's very little work done, then that means that I have a small change in energy. If there's a lot of work done, then you have a large change in energy. So what you want to pay attention that when you are thinking in energy units, you got to think about work. So you must think about how much work is done to get a feel for energy. A lot of work done, a lot of energy. Little work done, little energy. And so what we're setting you up to look at here is that there are parts of the lab that are going to specifically focus on these things here. The problem is that a lot of times people don't understand the word energy and get it mixed up with the word power. There is a difference between energy. Now, what do I mean by energy? Remember, it's the change in energy and power. So one way to think about this is we could say the following thing here. We can say here is that when we say energy, a lot of times we say that energy is stored work. How much work did you store in this process? So for example, if you eat something and you only eat a little bit, a lot of the times we say that you've eaten some food and you have stored food energy or calories in your body. So if you've eaten just a little bit or something that doesn't have a lot of calories, then the amount of work that you can do is going to be very little. However, if you store a lot of calories, for that day, then more likely is that you're not going to tire out, as they say. Now, note that these words are really poor, but for the sake of argument, that's how we typically look at that. On the other hand, we have this thing called power. Power is the rate at which work is done. And by the way, one way that we can look at this mathematically here is that we could say that power is how quickly work was done over time. But remember, another way of work, another word for work is also change in energy. How quickly was the energy changed per unit time? So there's a big difference between the two here. So if you think of energy, you got to think about work. If you think of power, it's about how quickly is energy or work being done. And when you look at these things, you're going to find that a big part of the lab is about the units of energy and power. So if I look at the units of energy, these go by the units. The SI units are joules. And it turns out that joules are tiny. So what we find here is that a more convenient unit is kilojoules. Because a joule is a very, very tiny amount of work. So the standard unit in this lab, for the most part, is kilojoules. Okay, it's a kilojoules. And it turns out that a kilojoule is about 4 food calories. So I would say, so I'm going to come back here and I'm going to say that this is about, let me make sure here. No. That's not correct. I'm getting my units mixed up. So a food calorie, okay, so 1 food calorie is about 4 kilojoules. So it's a convenient number to kind of keep in the back of your head that a food calorie is about 4,000 joules. It's a little bit more, sort of like 44.2 kilojoules, but we'll leave it at that. On the other hand, the units of power is what we call a joule per second. And this, by definition, is what we call an energy watt or a power watt. And a lot of times we write power in terms of W for watts. But again, a watt is not a good unit a lot of the times. So you have to look at the situation that you're dealing with. If you're looking at light bulbs, well, then you could talk about light bulbs by, in terms of watts, but what you're going to find here as you get to household energies, you'll be talking more in the language of kilowatts. So again, the units really matter. So if we're talking about everyday situations, then we're typically talking in units of watts. But if you're talking about like household energies, then these units should be written in kilowatts. Like your PG&E bill is written in units of kilowatts. So it depends on, the scale that you're actually looking at. So that's pretty much the beginning of the first part of the labs here. So one last thing that we want to do here is that we want to classify the types of energies. So we could imagine that we have a melting pot of, races here in the country, as they say, right? In the same way, we have a pot of energies. So we could imagine that if we were to take all of our energies and we have this pot, what we're going to find here is that in this pot, energy is energy. One cannot distinguish between one type of energy from another. So if I have a pot, and let's say I'm making a soup or whatever it is, once I put it into the pot, energy is energy. I cannot separate one from the other, sort of like if I'm putting spices in. Once they're all melded together, they're all the same. So when I say the word energy, it comes in different types. And what I'm seeing here is that as I start to classify these energies, one type of energy is called kinetic energy. This is the energy of motion. And then there's another type of energy. This is the energy called potential. This is the energy of changes in position. Now, I'm going to be careful here. This should be changes in motion. So everything has to be about changes because that's the definition of energy. And then there's also the energy of heat. So when we say the energy of heat, what we say here is that this is the change in molecular motion. And when we say changes in motion, and I say kinetic, maybe I should say that this should be changes in and macroscopic motion. So what is the change in molecular motion? Maybe I should call it microscopic motion. Maybe I shouldn't say molecular, but microscopic. And I can keep going on. And then there's some people that will then say there's food energy. Well, it turns out that food energy is a type of potential energy. And then we could then talk about the energy of light. And we can just keep going on and on and on here. But these are some of the things that we start to look at as we look at some of these things here. So now, here's what I'd want to think about overall. When you go through the lab, the idea is not to get hardcore numbers. The idea is to get a feel for what is going on. I expect that you don't know anything when you say the word energy. So what do you mean by the word energy? So let's just briefly go through each of the parts of the lab. And I'm only going to go through parts of it. Actually, I might go through all of it, but just go through it lightly. So now let's look at part one. So when you look at part one, we're going to look at energy units. So when you're looking at these, I wrote energy twice, energy units, what I want you to do here is the whole idea, the goal is to get a feel for a joule of work. Okay? That's a joule of work. So that means if you take what a joule of work is here, you're going to take a block, and this block is going to have a weight of 1 Newton. That's its weight. And what you're going to do here is that you're going to lift up this block to some height, and this height here is going to be a height of 1 meter. So when you do this work, this amount of work here turns out to be, it's going to be force times distance, which will then be 1 Newton times 1 meter, and this will then be 1 joule of work. So it turns out because we changed the height of this block, this is 1 joule of potential energy. But remember, when we look at the overall concept of energy, it's like a big pot. I can't distinguish between one type of energy from another unless I isolate it like this. So then we're going to ask you to pick up other objects and lift them and see how much work you did. However much work you did is then how much energy how much potential energy did you create in that? Also, you're going to be looking at food units in a very analogous way. Okay? So then part 2 here, we're going to look at power units. So if you're looking at power units, the whole goal of power units is to do what? The goal is to get a feel for a watt of power. Okay? What is a watt of power? And there's a couple ways to actually look at this. The easiest way to look at this thing here is that you can look at light bulbs or you could look at power appliances. So here, the first part that we're going to look at is we're going to look at the power used by electrical appliances. Now, the way we calculate power in appliances is that you're going to have to get a sense of some electrical quantities, but the way we typically write power for electrical appliances, it's something called the voltage times the current. And you can actually look these things up. So a lot of the times, the voltage in appliances is 120 volts. And here, they'll typically give you what the max current this thing can handle. So if you, just by looking at an apparatus, you can actually calculate what power is required. But that's too complicated for this course. So what we want you to do here is that we have a table of powers. And what do I mean by that? So when I look at this table, here's what I'm seeing. Let me go grab this. So you have this table, and what you're seeing here is that you have they're asking you to guess. So note, yes, this is a guess. And it's going to be, it may be hard to kind of, make a good guess, but the only way you can get a good guess here is that you got to make a lot of mistakes here. And that's okay. And so what you want to do here is that what you can do here is that by looking at the appliance, they should give you what the power is on that appliance. Now, if they don't give you the power, then using the voltage times the current that they suggest will then give you, they'll tell you what the power is by doing this way. But I think that probably the way Julia has it set up is that you have the automatic powers given to you. Now, once you make a guess, then try to get this from the appliance, the label that's there, and then use this thing here called a kilowatt meter. By the way, these are pretty awesome, and you can buy them from Amazon for a good one for about 20 bucks. There are some cheaper ones, but they don't work. But it tells you the power consumption, that's what it is. So then, when you're using the watts, you gotta make sure that this thing is set to watts so that you can measure watts. If it's set to voltage, then you're gonna get a voltage reading. You gotta click the watts button. So then measure these guys. And what you're doing here is that you're getting set to get a feel for what it means to operate. Now note that we have these blanks here, and these blanks are on purpose to see if you want to test anything else. And probably the other thing that's going to be really, very enlightening here is that now that you got a sense of these powers here, what you're going to find here is that you're going to have different types of light bulb powers. So in this situation, what you're really looking at is that you are then going to look at the powers of an incandescent bulb. Now remember, these incandescent bulbs, you probably have been noting that people don't want you to use this anymore. So they went from an incandescent bulb, and then technology got it to then we went to what's called a compact fluorescent. No, fluorescent is with the U. Fluorescent bulb. And then, of course, the modern bulbs are these LED bulbs. So the question is, why did this actually occur? And it has to do with the power. So the question is, where is the energy going? So is the energy going? So let me start all over again. So really the question that we're asking here is this: how much energy is used for light versus heat? And when you see that kilowatt device will show you why we now go to LED bulbs. Let's go to the next one here. This is part 3. In part 3, we're then going to measure your energy and power going upstairs. Okay? So that's what the goal is right there. So one of the things that you want to pay attention here is that in this situation, what we're looking at is that you want to set it up where you need to measure your energy here. And so what you're going to find here is that you're then going to ask the question, how much work did you do to go up a flight of stairs? So work is then going to be equal to your weight times the height that you went up the stairs. So the weight here, you want to then get your weight in newtons. And then here, you're going to have to measure with tape measure the height that you went up. So now what you've done here is that you have, so if you know your weight and you know your height that you went up, you now know how much work. So now to measure power, then your power is then going to be how much work you did in the amount of time that you did it here. So a nice way to actually think about this is that if you go up and down the stairs, remember, one measurement is typically not good. So you should do multiple measurements and then get a time average to get the average thing, the average time. And then you go and you calculate your power. So this is an important piece. So measuring this power is extremely important for part 4. In other words, don't do part 4 unless you've done part 3. Okay? Because you need to get a feel for your power in order to understand what part 4 is. You got to get a feel for that power. So then, here we go. So then let's go to part 4. And part 4, what you're going to do here is that now you're then going to, you're going to look at, I guess, bicycle power to light up bulbs. And when we talk about the bulbs, we're going to talk about incandescent. You've already got a feel for what incandescent means from part 2. Fluorescent, compact fluorescent. How do you spell fluorescent again? I think this is correct. Versus LED. And this one is an eye opener.